So you probably already know that in two dimensions, to which we are confined anyway. So this is the real axis, this is the imaginary axis, a point xy. You can associate a complex variable to it. Z is x plus iy, and then this is r, which is also equal to mod of z, and this angle is theta, which is called the argument of z and is given by tan inverse y by x. So this is, if this is x plus iy, then the mirror image about the real axis, this point is called z bar, which is x minus iy. It also has an absolute value of r, whereas this angle is minus theta. Okay, this can also, this complex variable can also be expressed as r e to the power I theta, and z bar can be expressed as r e to the power minus I theta. The magnitude of z, mod z, is equal to root over x square plus y square, where x is the real part of z and y is the imaginary part of z. This is how we will denote the complex variable. Then r can also be r can also be expressed as r square equal to z bar, because that is equal to x plus iy into x minus iy, which gives you x square iy times iy is I square y square minus I square y square, but I square is minus 1, so x square plus y square. So root of that is equal to r. This is also something that you must be aware of already. So now we are going to look at functions of complex variables. So f of z is a function of z, which means it has a real part, which is a function of x and y. It has an imaginary part, which is also a function of x and y. Now, x, y, z, and z bar are related. So, z is equal to x plus iy. Z bar is x minus iy, which implies that x is half of z plus z bar, and y is equal to 1 by 2i z minus z bar. So this is easily obtainable from these two. So any function of xy can also be thought of as a function of z and z bar, and that means that derivatives with respect to x can be expressed in terms of derivatives with respect to z and z bar using the chain rule of partial differentiation. Similarly, derivatives with respect to z and derivatives with respect to z bar are expressible in terms of derivatives with respect to x and y. Let's see just one case. Let's see this. The others are derived in the same way, but we have to remember these equations. These relations are very important. They'll keep coming back. So if you now want del x of something, that would be del z del x plus del z bar del z bar del x. But from here, del z del x and del z bar del x both are equal to 1. So del x of something can be written as del z of the same thing plus del z bar of the same thing. So this is how del x can be written. Similarly, del y. If you want to do the other way around, so you want to have del z of something, so you want del z of something, then you write it as del x of so you write it like this, and then del x del z is half, del y del z is 1 by 2i. So this would become half del x plus 1 by 2i del uh, del y, and you multiply this by, you write it as I square and make this minus. So minus I square is, I square is minus 1, minus of minus 1 is 1. So I cancels. So you can write it as half of del x minus I del y. Similarly, you can write del z bar of something uh, in the similar way as this. So these are when a function is given in terms of x and y and we want to derive its z derivative and the z bar derivative, we use these two. And when a function is given in terms of z and z bar and we want to derive its x and y derivatives, these are the expressions that we use. Okay. So here's an example. A function fz is az plus bz square, where a and b, let's say, are real numbers. In that case, in place of x, in place of z, I can write x plus iy. In place of z square, I write x plus iy whole square. And then I can split it up into real parts and imaginary parts. This is pretty simple to do. So this is my uxy, and this is my vxy. Okay, so real part of f will be this function, imaginary part of f will be this function. I think this is absolutely clear to you from what you know about complex variables already. Now we come to the question of analytic functions. The concept of analytic functions is going to be very important for us, and analytic functions are a very important concept in mathematics as well. So given a function of z, fz equal to u plus iv, at a point z equal to x plus iy, I can derive f prime z, which is del z of u plus iv. So to do that, what I do is I use the formulas for del z. So del z is del z half del x minus I del y. So use that, half del x minus I del y of u plus iv, where remember u and v both are functions of x and y. If you do that, then this is what you get. You get half del u del x plus I del v del y minus I del u del y minus I square del v del y. So minus I square is minus 1, so this becomes plus and this disappears. This is what you get. Take it into take the imaginary and real parts separated. So you have del u del x plus del v del y as the real part. This is the real part of f prime z, and this is the imaginary part of del f prime z. So now let us try to look at the condition where this exists, f prime z exists at the point z. If f prime z has to exist, then no matter which way we approach the point, so here is my imaginary axis, there is my real axis, and here is z, where I want to see if f prime z exists, then no matter which way I approach z, I should get the same answer from this operation. In particular, if I approach from this direction or I approach from this direction, I should get the same answer. Okay. Now let us approach along the real axis, the x-axis. If I approach along the x-axis, then the y doesn't change, so this does not change, this does not change. So f prime z should be half del u del x plus I by 2 del v del x. So this should be. On the other hand, if I approach along the y direction, then this should not be there. This should not be there, and f prime z should be half del v del y minus I half del u del y. Okay. Now, for f prime z to exist, and which is another way of saying that f prime z is analytic at z, this and this have to be equal. To be equal, I must have the real parts equated and the imaginary parts equated. So del u del x must be equal to del v del y, and del v del x must be equal to minus del u del y. And if that is true, then the function fz is called analytic, which means its derivatives exist at it is analytic at z, and its derivatives exist at z. Okay, so the condition for analyticity of a function, or a function of complex variables to be to have derivatives at a particular point, its real and imaginary parts must satisfy these two equations, del u del x equal to del v del y and del u del y equal to minus del v del x, which are called the famous Cauchy-Riemann conditions for analyticity of a complex function. And if it is analytic at z, then del u del x plus I del v del x will be equal to del v del y minus I del u del y. This is the derivative that we got while moving along x, and this is the derivative we got while moving along y. These two should be equal. Now, there's one more thing that you probably already know, but we will talk about it anyway. So these two equations, from these two equations, what we can also see is that, let us write del square u del x square. So take derivatives with respect to x once more. So you get that should be equal to del square v del x del y, and here let's write del square u del y square, derivative with y once again, and that should be equal to minus del square v del x del y. For a continuous function v, this guy and this guy are the same, which means that del square u del x square plus del square u del y square is equal to 0. So this is denoted by the harmonic with respect to the harmonic operator del square. So del square of u has to be equal to 0. Similarly, if you do a derivative with respect to del del y here and del del x here, the second equation, you come to the conclusion that del square v is also equal to 0, which means that if a function is analytic, its real parts and its imaginary parts separately satisfy the harmonic equation. So that is another test of analyticity, that u and v both satisfy the harmonic equation. Okay, there's one more relation, but before that, let us get some notations in place. So we will denote the space of all complex numbers. C is a big bag which contains all the infinite kinds of complex numbers that we can have. And if fz and gz are analytic functions in some part of C, we call that U, then alpha fz is also analytic, fz plus gz is also analytic, fz times gz is also analytic, and fz and gz are analytic provided that gz is not equal to 0. If gz is 0 at some point, then of course it's not analytic. Otherwise, fz by gz is also analytic. Okay, so remember this, that fz multiplied by a constant is analytic, fz added to another analytic function is analytic, multiplied is analytic, divided is analytic, provided gz is not equal to 0. And the most reliable analytic function, which is analytic on the entire complex plane C, is a polynomial of this form. This is also a fact that you have to remember, because we will deal with series of complex numbers quite a bit. So a polynomial is a guaranteed analytical function that is analytic over the entire complex plane C. Okay. Uh, so analytic functions are very special. So analytic functions are functions that possess derivatives, and at a point, at least in some region, if not in the whole plane C, at least in some region of C, they possess derivatives. That's why they are called analytic. And analytic functions are rare. Analytic functions are rare. They are rarer than their real counterparts. Complex analytic functions of complex variables are rare. There aren't many of them, but when they exist, they have very, very special and remarkable properties. For example, we will see that we can do several things with it. For example, one of the things that we will do is in the neighborhood of a point where a function is analytic, we can always expand it in terms of a Taylor series which is convergent. Also, if we know the values of this function fz, analytic function fz over a contour, over a closed curve, then we know the value of it at any point inside the closed curve. So if we have a closed contour and we know the value of fz at this point, we know the value, then we know the value at any point inside. This is absolutely remarkable. This doesn't happen for real functions. And then analytic functions appear in solutions to problems in physics, and they are sometimes analytic only over, say, a restricted domain. And then we can continue this function. We will learn how to do that by doing something called analytic continuation. We can continue this function and piece together another function which is analytic over a larger domain. So we can expand the domain of analyticity of this function by piecing it together with another function in a method which is known as analytic continuation. So this makes analytic functions very useful and very remarkable at the same time. They have some more properties. One of the properties is this. Let us see what this means. So to do this, let us define a function which is conjugate of f. So conjugate of f, remember fz, remember, is u plus iv. So f bar z is u minus iv. Okay. So now if fz is analytic, then if fz is analytic, the Cauchy-Riemann conditions are satisfied, which means that del u del x is equal to del v del y, and del u del y is equal to minus del v del x. So these two are the Cauchy-Riemann equations. That is satisfied for u and v. And then let us try to get the del z of fz. What is del z? Let's go back. So del z is half del x minus I del y. So we will do half del x minus I del y of u minus iv. If we do that, then this is what we will get: half del u del x. Let's take the real parts first. This will give a real part, so you'll have minus del v del y. This will be the real part, and the imaginary part will be I times del u del y and plus del v del x. So this will be, now this is analytic, so u and v satisfy these two equations. So del u del x and del v del y should be equal, so this part is 0, and del u del y and del v del x should be negative of each other, so this part is 0 as well, which means that del z of f bar z is equal to 0, which means that f bar z is a function of z bar only. F bar z is not a function of z, f bar z is a function of z bar only, and we will often denote f bar z by f z bar by this. So this will mean f z bar, which we now know is a function of z bar only. Okay. In a similar way, we can show that fz is a function of z only. Fz is a function of z only. It's not a function of z bar. So that is also easy to show. You show it exactly in the same way. Okay. So another quantity that we will often encounter is called the associated function of fz, and is defined as fz bar, function of z bar, conjugate of that. So what does that mean? So fz is an analytic function, which is u plus iv, and then you evaluate it at z bar. So that will give you u x minus y plus I v x minus y. So this is what evaluating it at z bar means. Now if you take bar of this, the whole thing, then you will change this to minus. Now this is the quantity that we have. So this is u evaluated at x minus y minus v evaluated at x minus y. Now what we are going to show is that this function does not depend on z bar. This is not a function of z bar. To do that, we will take del z bar of this. We'll take del z bar of this, and again go back. Look at the expression for del z bar. It's del x plus I del y. So what we are going to do is half del x plus I del y of ux minus y minus I v x minus y. This is what we will do, and that's what is done in this case. And if you do this, you will see that this is equal to 0, and therefore f z bar bar, which is the associated function of fz, is also analytic and is also only a function of z, not of z bar. So remember this, fz is a function of z only, fz bar is a function of z bar, fz bar is same as f this, and then this is the associated function. This is a function of z and is also analytic. Okay. So so if I now define two domains, say I have a complex plane, and then I have some region in the complex plane which I denote by S plus. The easiest example is let us write the upper part is S plus and the lower part is S minus, let's say, and then in the upper half plane you have fz defined. And it is analytic in the upper half plane. Fz bar, remember z bars all lie here, z bars all reside here. So fz bar is a function that is defined in the lower half plane S minus, and so does fz bar. So what it means is fz is a function which is analytic in the upper half plane. Fz bar is a function which is analytic in the lower half plane. So this is what an associated function is good for. So given a fz bar in the which is analytic in the upper half plane, you can define a fz bar, an associated function, which is automatically analytic in the lower half plane. So if fz bar is analytic in a region of the upper half plane, then fz bar, the associated function, is analytic in the mirror region, mirrored region in the lower half plane. So that is what fz bar is. So these are two concepts that we will use quite often. So what we have established is fz is not a function of z bar. So del z bar of fz is equal to 0. Fz bar is not a function of z. So del z bar of fz bar, this one, is equal to 0. This is a function of z. So this del z bar of this is equal to 0. So this is analytic, but this is defined in the lower half plane. So that's why it's called an associated function. There are many functions which are multiple valued. So for example, argument of z is a multiple valued function. Why? Because if this is z, this angle is the argument of z. So argument of z is argument of z lies between minus pi and pi. So it from here to here is pi, here to here is minus pi. So the argument of z, this angle theta, lies between pi and minus pi. Now it is discontinuous at this negative x-axis because it jumps from pi to minus pi across this. So it is a multiple valued function because you come round one full circle, its value changes here. So if you go around, it goes to minus pi, then minus 2 pi, come back again, its value changes. So you can go around many times, and every time its value changes. So it is a multiple valued function, but it is an important function that we are going to use quite often. So these are easy to prove. These conditions are easy to prove. So start with argument of z is tan inverse y by x. Start with that, and then you can prove any of these, all of these, quite easily. Not going into the proofs, but remember that arg z is our first example of multiple valued functions, and it has these important properties. There are other multiple valued functions that we are going to encounter. For example, one of the multiple valued functions is log z. So w is a function which is log z. Remember, z is r e to the power I theta, but this can also be written as r e to the power I theta plus 2n pi. Right? Every time you come back 2n pi, you get, every time you come back 2 pi, you get the same values of, remember, e to the power I theta is cos theta plus I sine theta, right? And e to the power I theta plus 2n pi is cos theta plus 2n pi plus I sine theta plus 2n pi. So this is equal to sine theta, obviously, and this is equal to cos theta. So these two things are actually equal. So r e to the power I theta and r e to the power I theta plus 2n pi are the same things. So for n equal to 0, plus minus 1, plus minus 2, and so on, you have, now if you take log z of this, log z of this quantity, then you get log r plus log e to the power, this would be log e to the power I theta plus 2n pi, but log of this quantity is just I theta plus 2n pi. So log z is this quantity, which takes a different value depending on the value of pi that you take. The first time n is 0, so it takes some value. Then n equal to 1, it takes a different value. N equal to 2, it takes a different value. You can go in the negative direction also. it will keep on taking different values, though z would come back to the same value for every 2 pi. Okay, so log z is a typical example of a multiple valued function which will change values every time you go around 2 pi, around the origin. Okay, uh, so we can choose, for example, we can choose for such functions, we generally choose a principal branch. What we say is this function has different branches. So imagine n is equal to 2 pi, or n is equal to 0, let's say. Let's start with n equal to 0. So this is real, this is imaginary. So n equal to 0 means I go once around this, right? I go once around this and stop. So then log z is single valued. As long as I don't increase the angle beyond 2 pi, or I remain within plus pi and minus pi, which is the same thing. So I remain within plus pi. So this is plus pi, and this is minus pi. So I remain within plus pi and minus pi. Provided I do that, then log z is single valued. It doesn't change values because you are not going beyond 2 pi. So that is called the primary branch of this function. Okay. If you have n equal to 1, that's another branch. If you have n equal to 2, that's another branch, and so on. So as long as we remain within this plus pi and minus pi, we have a single valued function. To do that, what we imagine is that I cut the domain along the negative x-axis and gouge a small hole around the origin. So I cut the domain like this. So here my angle is pi, here angle is minus pi, but my domain is cut here, so I cannot cross this line. So my domain is now a slit domain. So I slit the domain, and this is called a branch cut. So what a branch cut does is it modifies my domain over which the function is defined. It modifies the domain in such a way that a function is single valued. And so another important multiple valued function is w z to the power alpha. Now we can write this as exponential alpha, exponential log of z to the power alpha, which is equal to exponential alpha log z. Now log z we already know is log z we already know is this. So, and it's multiple valued. So this would be exponential alpha log r plus alpha I theta plus 2n. So this would be your w. This is, of course, can be written as w can be written as, take these two terms, and write the first one, and then the second one comes from 2 pi I n, this n here, 2 pi I n alpha. 2 pi I n alpha is this term. So this is the term that's making it multiple valued. We've already seen that this is not multiple valued, this is single valued function. So if alpha is an integer, alpha n is also an integer. So this is equal to 1 if alpha is an integer. So in that case, w is single valued. If alpha is an integer, it has only one value. However, if alpha is of the form, let's say a plus ib, then e to the power 2 pi alpha ni can be written as this. So it will take a new value for every value of n. as you remember, 0 plus minus 1 plus minus 2, etc. So it has infinite values. And if alpha, therefore if alpha is non-integer, or if it's complex like this, then it has multiple values and infinite number of values. It's multiple valued function. Z to the power 1 by k, kth root of z. Kth root of z is, so z can be written as r e to the power I theta plus 2n pi. So z to the power 1 by k is r to the power 1 by k, this divided by k. Now when k is equal to n, then this becomes theta plus theta by n plus 2 pi. So e to the power theta by n plus 2 pi is equal to e to the power theta by n. Okay, but when k is not k is 0 to n minus 1, then this has different values. And therefore z to the power 1 plus k has n branches. It is n valued, going from 0 to n minus 1. At k equal to n, it comes back to the value at 0. So till then it has different values. Okay. These are some pictures taken from Wikipedia. So this is your log z, imaginary part of log z. So so each color is a different branch. So you go round once the origin. Remember, it is I theta plus 2n pi I think. The imaginary part is this. Yeah, theta plus 2n pi. The imaginary part is theta plus 2n pi. So this is the imaginary part, theta plus 2n pi. So as theta increases from minus pi to pi, you go up. Then you go to the next branch for n equal to 1, that's the red branch. Then you go to the yellow branch, and so on. Of course, these extend to infinity, and we have shown only a small box. So it's like a spiral staircase that goes up about the branch point, which is your z equal to 0. Similarly, this is z to the power half. We have seen z to the power 1 by k. So z to the power half has two branches, which is this and this. So again, you go around. So you go around 180 degrees, and then your branch changes. You go into the next branch. Then you go around like this, and you come back to where you started from. You come back to z equal to 0. This is 1/4. It has 4 branches. So the green, the blue, then the yellow, and the red. So these are the 4 branches of z to the power 1 by 4. And at the end of the 4th branch, once you've gone round the 4th branch, you come back basically to z equal to 0. So you come back to the green branch again, which was the first branch. So these are called Riemann surfaces, which is a way of showing, a way of drawing complex functions. Okay, you can easily do this on MATLAB. If you are interested, you can try for other functions, and sometimes you get really beautiful pictures. So the next concept that we are going to talk about is contour integration, and you probably are aware of it. But contour integration is integration of a complex variable along a given curve. So this is what a contour integral will look like. I want to integrate fz dz from z1 to z2. But in case of a complex variable, I need to be told what is the path by which I go from z1 to z2, which is not the case for a definite integral that you do in calculus. So suppose I am given this function. This is a complex function, and I want to integrate it along this path. Okay, from t equal to 0 to 1. That's what I want to do. And then I know what to do. So I evaluate fz. So f, in place of z, I put t plus it, and that gives me this integral, which I can easily integrate from 0 to 1 to get 2I by 3. So this is pretty simple. So what I have done is I know that I'm going along z equal to t plus it. Therefore, dz is dt plus 1 plus I. It's usual integration, and I evaluate fz, which is this. I evaluate fz, and I do the integral. So uh, take a more important example that we are going to come back to. Fz is 1 by z. Fz is 1 by z, and I want to integrate it over a circle. So on a circle, z is equal to r is the radius of the circle, e to the power I theta. So as you go around a circle, only theta changes, r is fixed, which means dz is r I theta e to the power I theta d theta. So from I want to integrate fz dz over a circle C. So I will evaluate 1 by z dz over the circle C, which I can now write as C is 1 by r e to the power I theta, that's it in the circle, times dz, which is r e to the power I theta I theta I d theta. I think I d theta, not I theta d theta, I d theta, I d theta. So this guy cancels out, and then I am left with, so I go, theta goes from 0 to 2 pi, so I am left with 2 pi I. So the integral of 1 by z over a closed circle is equal to 2 pi I. So remember this result, that fz is 1 by z, fz dz over a circle of radius r is equal to 2 pi I. This is a very, very important result, and we will come back to it many times. Now, before we go further on doing these integrals, which are a very, very important part of complex variable theory, because there are several theorems that are based on this, let us distinguish between contours, domains, simply connected, and multiply connected regions. So this is a domain D, which is surrounded by this contour C. So this contour C encloses this domain D, and the contour is traced in such a way that if you walk along the contour, the domain is always to your left. So it is always traced in a clockwise direction. A clockwise direction contour traced in the clockwise direction, and it's always traced in the anti-clockwise direction, and a contour traced in the anti-clockwise direction is a positive contour. So D is the domain, and D is called a simply connected domain, because if you draw a curve inside D, any curve inside D, you can shrink this curve to a point without ever crossing D, and that applies to any curve. You draw it here, you can shrink it to a point without ever crossing D. On the other hand, this D is multiply connected, because obviously if you have a curve like this, which encloses the hole in the domain, then you cannot shrink this curve to a point without ever crossing the boundaries of D. So this is a multiply connected domain. And this is a simply connected domain. Okay, let us do a problem. Let us evaluate fz equal to log z. So what we want to evaluate is fz dz is equal to log z dz over the unit circle So on the unit circle, the radius is 1. So this, any point on the unit circle is e to the power I theta. E to the power I theta. And remember, log z is a multiple valued function. So to make it single valued, we take this branch cut around this branch point at z equal to 0, so that the log z cannot go into, log z is confined to its primary branch and cannot go into the other branches. So it is basically a single valued function once you have made the branch cut. So to integrate it from over the unit circle, we have to integrate it up to a point very close to the negative real axis. So we have to, this angle is pi minus epsilon, and a point very close to the, just below the negative x-axis, which has an angle of minus pi epsilon. So z is always e to the power I theta, which means dz is I e to the power I theta d theta. So this is dz. So this is what we have, as dz. This is log z, and log e to the power I theta is just equal to I theta, and then I theta and I multiply to give you this minus. So this is minus theta e to the power I theta d theta. This is not dt, this is d theta. So now you can do an integration by parts. Take this limit, this is just an integration by parts of this function, x e to the power ix kind of function. And then as you take the limit, you remember that e to the power I pi and e to the power minus I pi both tend to minus 1, because e to the power I pi is, remember, cos pi plus I sin pi. So both of them will tend to minus 1, because sin pi is equal to 0. This is equal to 0. Both of them is equal to minus 1. Using that limit, you will come to the conclusion that log z dz is equal to minus 2 pi I. Another result that we need to remember very, very carefully. So about a unit circle, about the origin, log z integrates to minus 2 pi I. 1 by z integrates to 2 pi I, remember, about any circle. Right. So this is our first theorem. It's called the Cauchy integral theorem. And we will state a few theorems, 3 theorems actually. We will not prove them, but you can find the proofs in any book on Kreyszig or any such book. So here goes the first theorem. So D is a subset of the complex plane, and within this D, Fz is analytic. Fz is analytic within D. Then if you take any closed contour gamma, any closed contour, and take a integral over this closed contour, that integral will always be equal to 0. So if Fz is an analytic function in that domain and your contour lies completely within the domain, so if your contour encloses no point where Fz is not analytic, then the contour integral is 0. This is a very, very powerful statement. So let's see how this is used. So let's go back to our friend Fz equal to 1 by z that we have looked at, and we have found it on a circle C. So we have already seen that when integrated over any circle C, it gives 2 pi I. Now the question is, if I integrate it over this ellipse, what should it give? Now to do that, let us do a trick. We have this ellipse over which we have to evaluate 1 by z, but then let us put a circle just above the ellipse so that these points match. So our contour now is this, and this. So this contour, I'm always going anti-clockwise. So this contour never encloses this point where 1 by z is non-analytic. 1 by z is non-analytic at z equal to 0. So over this entire contour, it has to be equal to 0. So Fz 1 by z dz over this whole contour, which we call C, is equal to 0. Now, C is composed of C1, which I have traversed in an anti-clockwise direction. Then it has E, which I have traversed in a clockwise direction. That's why I have this minus E. And then again C2, which I have traversed in a anti-clockwise direction. So it is plus C2. So over this contour, this is equal to 0. Okay, and I already know that over the contour composed of C1 and C2, it is equal to 2 pi I. So the integral over E is equal to the integral over C1 and C2, which I already have derived to be 2 pi I. So 1 by Z over the ellipse is also equal to 2 pi I. Extending this, I can say that if I take any contour around the origin, and integration of 1 by z dz over this contour that encloses the origin, goes round the origin, will always be equal to 2 pi I. So if you go once round the origin, if your contour goes once round the origin, then 1 by z will always integrate to 2 pi I, which is again a very, very powerful statement. This 2 pi I does not, though we have proved it for a circle, it does not depend on the shape of the curve. It is always equal to 2 pi I provided you encircle the origin. Okay, this we will prove from, this we will see from another perspective when we do the residue theorem. This quantity is basically called the residue of this function fz. Let us look at this problem. So this is not 1 by z but 1 by z minus z naught, which has a point of non-analyticity at z naught. So I have to evaluate it over a contour which is centered at z naught. So z naught occurs inside the contour gamma. Now to apply Cauchy theorem, what I do is I make a cut here and a cut here, and I consider two contours. One is this 1 4 4 3 3 2 2 1, and the other is this 4 1 1 2 2 3 3 4. Now note that C12 and C21 are traversed in opposite directions. 3 4 and 4 3 are traversed in opposite directions. No points of non-analyticity in the top contour, so the integral over this is 0. Over this is also 0. There are no points of non-analyticity. That's only here, so that is excluded. So both of these two are 0. So I can now write them separately. So this is what I do. This is for the lower contour, that's equal to 0. For the upper contour, that is equal to 0 as well. Add them together, then 1 2 2 1 and 3 4 4 3 cancel out, because remember they are traversed in opposite directions, and this is what you are left with. Out of this, 1 4 and 4 1 together, so 1 4 and 4 1 together give you your contour gamma, whereas 2 3 and 3 2 together give you a circle. So this gives you a circle. So the fz over gamma has to be equal to fz over the circle, and I know that fz over the circle is 2 pi I. So fz over gamma has to be equal to 2 pi I. So that's another important result, that not only is it if the point of non-analyticity is at the origin, do we get the result that the integral is independent of the contour that I take. If I take any contour around the point of non-analyticity, I always get 2 pi I. So if I go around any point of singularity z naught, I will get 2 pi I. Okay, so this is a very, very important result, and you must remember this. So now let us look at an extension of this. So so far we have seen that so far we have looked at the Cauchy integral theorem, and now this is known as the Cauchy integral formula. Uh, it's you can confuse it, but please don't. Uh, the nth derivative at some point z0 that lies inside the domain. So this is my contour gamma. This is the domain D. The function is analytic here. It's an analytic function. Take a point z0 and I can get the nth derivative of the function at this point if I know the values of the function on the contour itself. This is the theorem that I alluded to at the beginning when I talked about analytic function. This is a very, very remarkable result which says that the nth derivative at z0 anywhere inside the domain where the function is analytic is given by this formula. Okay. In particular, if n is equal to 0, then I have 0 factorial 1 by 2 pi I contour integral over gamma of f zeta, zeta minus z0 d zeta. This integral gives you the value of f0 z0, which is the value of the function at z0. So the value of the function at z0 can be known if the function is known all over the contour. And this result is extremely powerful, extremely counterintuitive, that if you know the values along a contour, you know the values inside the contour as well. So not only you know the values, you also know the values of all the derivatives of the function, So this is practically, this is very important to evaluate contour integrals. And for example, take a contour integral of this form, right? E to the power 5z by z cube dz. Okay, so go back to this formula. Let's take n equal to 2, z0 equal to 0. Okay, n equal to 2 gives me zeta to the power 3. Let's take fz to be e to the power 5z, right? If I do that, then the third derivative, second derivative, f2 of f2 is so df dz is 5 e to the power 5z, d square f dz square is 25 e to the power 5z. So this is 25 e to the power 5z, but it is evaluated, remember, at z0. Z0 we have taken as 0, so this goes to 1, so this is 25. So, and this is 2 factorial, so I have 25 equal to 2 factorial by 2 pi I, and this integral over gamma of e to the power 5z divided by z cube dz. This is what I am supposed to evaluate. Then I have 25 pi I is equal to e to the power 5z by z cube dz. So this integral has a value of 25 pi I. So this is a very simple way of integrating. If you remember the Cauchy integral formula, it's a very simple way of integrating integrals of this form. Okay. Right. The last theorem is the residue theorem. The residue theorem is a generalization of all this. So just imagine that now the function is not completely analytic over this domain that is enclosed by C, but it has a finite number of points of non-analyticity. For example, here, these are points of non-analyticity. Then the integral is not equal to 0. If these points were not there, remember, it would be equal to 0. It's not equal to 0, but is equal to 2 pi I times the residues calculated at this point. Sum of the residues calculated all this point. If there are n points of non-analyticity, n singular points, then the residues calculated at this point will, sum of the residues calculated at this point will give you the contour integral. So you not only can evaluate the contour integral if the domain has is analytic in the domain, you can even evaluate it if z has isolated points of non-analyticity or singularity inside the domain using this residue theorem. How do we calculate the residue? The residue is calculated in this manner. So the residue of the function is calculated if we have to see what is the order of the residue. So if the residue is of the order 1, then you multiply by z minus zk fz. You multiply fz by z minus zk, take the limit z tending to zk, and that's how that gives you the residue at the point zk. For example, I had this function fz equal to 1 by z. This has a residue of the order 1 because the power of z is 1. So if this has a residue of order 1, then and it has a singularity at z equal to 0. So I multiply it by z minus 0, 1 by z. So the residue comes out to be 1. So therefore there's only one singular point. So by the residue theorem, over some curve fz dz will be equal to 2 pi I times 1, which is equal to 2 pi I, which is a result that we have seen before. So the residue theorem only reiterates that result, but this is a very, very elegant way of getting to the integral, and also realizing that this 2 pi I does not depend on the nature of this curve as long as it encircles the origin. Okay. Now, in general, if you have a pole of order n, a singularity of order n, then you have to multiply the function with z minus zk. If zk is the point at which it is singular, z minus zk to the power n, the function has to be multiplied by this. The n minus 1th derivative has to be taken, and then you have to put the limit z tending to zk. That would give you the residue in the general case where you have a pole of order 1. That means the singularity is such that you have this n is greater than 1. So you have a function of this form. When you have a function of this form to integrate, then you have to take the n minus 1th derivative of the function multiplied by z minus zk, where zk is the point at which the function is not analytic or function is singular, which is also called a pole. A pole is a point at which the function is singular. Okay, so this theorem allows us to derive integrals, calculate integrals which are which are difficult integrals to do, and it allows us to calculate the principal values of integrals which have infinite domains. So for example, if I want to calculate an integral of this sort, what I do is I convert this. So this is an integral in a real variable x. So I convert this into a contour integral. I convert it into a contour integral over this domain that goes from minus rho to rho over 0. It comes back here. So I construct this imaginary domain gamma plus Cp and calculate, in place of fx, I calculate fz dz. Okay, and now I make rho go to infinity. In that case, I can set up this integral rho going to infinity fz dz is fx dx, because this is the real axis. So z is equal to x here. So fx dx from minus rho to rho, and then fz dz over this circle. So fx dx from minus rho to rho, this is the integral that I'm supposed to calculate, and then 0 to pi, only the upper part, 0 to pi. Remember, on this circle z is equal to rho e to the power I theta, and therefore dz is rho I e to the power I theta d theta. So that's what I have put here, and f is a function of rho e to the power I theta, and I know that now this integral by the residue theorem will be 2 pi I plus into the sum of the residues of the function that lie within that domain, uh, gamma plus rho, gamma plus c. Okay. Now what this means is that if I can find the residues, I can find the residues, but the whole thing hinges on the fact that this guy should go to zero. This guy should go to zero as my rho tends to infinity, which means that as I push these 2 points further and further away from infinity, then if this function goes to 0 in that limit, then the 2 pi I times the sum of the residue is equal to fx dx minus infinity to infinity. So that is what will happen if this goes to 0. When should it go to 0? It will go to 0 if f rho is a f rho e to the power I theta is a function of the decaying type, which means that the modulus of f uh, should decay as rho tends to infinity. If it's a function of this type, then obviously this will tend to 0 in this limit. In this limit, this will tend to 0, and your 2 pi I times sum of residues will be fx dx minus infinity to infinity. So we can't do this for every function, but for functions whose modulus are of the form this, for example, where mu is greater than 1, if the function's modulus is of this form, then it is of a decaying type, and this integrand will go to 0 as rho tends to infinity. So let us look at one example. Let us look at this integral. This will be difficult to integrate but we convert it into a complex integral. So just replace x by z, so 1 plus z square, and then this is of a decaying type, because as rho tends to infinity, this will tend to 1 by z to the power 4, which is a decaying function, and thus this integral will simply be 2 pi I sum of the residues of fz inside the contour, inside this contour. And if you look at the residues of this function, you have to see where its singular points lie. So this is a singularity. This has singularity at plus minus I. So z equal to plus minus I. It has poles, and the poles are of the order 2. Okay. So we have to use the residue theorem formula here. We have to use the residue theorem formula with n equal to 2. So we have to take the first derivative of z minus I to the power 2 fz and dz of that, limit z tends to plus minus I. So this is minus plus, and 1 by 1 factorial. That will give you the residue, which you can easily calculate. And if you do that, you will see that the residues are 1 by 4i. You have to calculate the residue only at I, because minus I does not lie inside the contour. Only I lies inside the contour. So you have to calculate it in I, and at I it will be 1 by 4i, and if you then put it back, multiply it by 2 pi I, you get I equal to pi by 2. So this integral is equal to pi by 2. The principal value of this integral is pi by 2, and the residue theorem allows you to find the value of the integral quite easily. Okay, so this is all about analytic functions, contour integrals of analytic functions. So what we have learned so far is that if a function is analytic in a particular domain and you have a contour enclosing it, then the integral over that contour is always equal to 0. If inside the contour there are no poles, then it's equal to 0. If there are poles, then it's equal to 2 pi I times the sum of the residue. The contour integral of a function over a contour enclosing a region where a function has a finite number of poles is 2 pi I times the residue. There's a way of calculating the residue, and that you have to know. Similarly, if you know the value of the function over the contour, you know the value of the function as well as its derivatives inside the contour as well, provided the function is analytic everywhere inside the contour. So analytic functions have this remarkable property that if you know their values over a contour, you know their values anywhere inside the contour. You know the values of their derivatives, nth derivatives, everywhere inside the contour. Okay. They have another remarkable property which I also alluded to, which is that if a function is analytic in a disk defined by this, so remember mod z minus z naught is a circle. So this is z. So mod z minus z naught is a circle that is centered at z naught. Okay, this is mod z minus z naught. This is the region mod z minus z naught. So this is a disk. In this disk, the function fz is analytic. And if it is, then it can be expressed at any point inside this, at another point. So another point away from fz, another point away from z naught, it can be expressed as a Taylor series which will converge to the value of the function at fz. So using the value at fz naught, you can express the function at fz. So this series, this infinite series, is guaranteed to converge to the value of the function at this point, if the function is analytic in the domain. In a domain of analyticity, you can always expand the function in terms of a convergent Taylor series. That is another remarkable property of analytic functions. Okay. If it is not analytic, if it has isolated points of analyticity, then you can expand it in terms of a Laurent series, So this Laurent series will converge to the value of the function, provided you evaluate it in an annular domain that does not include the pole where it is not analytic. So if you define it over this this annular domain, which inner radius small r, capital radius, outer radius capital R, if you expand it here, so if you have a point z here, the functional value here is fz, and this Laurent series is guaranteed to converge to the value of fz, provided z lies in this annular disk. Okay. The difference between the Laurent series and the Taylor series is that the Taylor series contains only positive powers of n, whereas the Laurent series also contains the negative powers of n. The coefficients of the Laurent series are given by this. This is a contour integral over gamma, where gamma is any contour that lies completely within the annular region. So any contour lying in the annular region can be used to evaluate these ANs, and then this series is guaranteed to converge to the value of the function at any point z inside this annular region. So these are statements that we are making without proving them, but these are very, very powerful statements. The first statement is that any analytic function in its domain of analyticity, the functional value at any point can be given in terms of functional values at another point in terms of a Taylor series that is guaranteed to converge. For a function which is not analytic at z0, I can make an annular region, and any point within the annular region I can give the functional value of fz at any point in the annular region in terms of a Laurent series, whose coefficients are generated by this formula here. So I won't do this problem. I leave it to you. It's actually part of the problem set that I'm going to give you. So this problem we might discuss in the class, or you might try it on your own. So what it says is that find the expansion of fz over the disk z minus 1. So the disk z minus 1 is a circle centered at z equal to 1. So circle centered here. So you have to find the expansion within this circle. Within this circle, log z is analytic because this circle does not contain the branch point at the origin at which log z is not analytic. So over this, you should be able to expand it in terms of a Taylor series about z equal to 1. So z naught is going to be equal to 1, and you can expand it in the Taylor series, and then this is the series that you will get. This is the series that you will get. This is the series expansion of log z that is valid inside this domain. Another problem that we are not going to do, again, this function has a singularity at z equal to 1. So we want to evaluate it over a disk mod z less than 1, which is this disk centered at the origin. It is this disk. Okay, and z equal to 1 is excluded, so it is again analytic over this disk. And if you can expand it as a Taylor series over this about z equal to 0. So if you do that, then you will find that the Taylor series expansion is simply 0 to infinity z to the power n, which converges to 1 by 1 minus z in this disk. In this disk of where it is analytic, it converges to 1 by 1 minus z. This is another very important result that we will use at certain points. Now do this problem. This is a problem that I'm going to definitely leave for you. So this function has two poles, z equal to 1, z equal to 2. Now what happens when you integrate it, when you try to expand it in this disk? So z less than 1 is this disk. Z lying between 1 and 2 is this disk, this annulus, right? And z greater than 2 is the region outside. So the poles are here and here. These are the two poles, z equal to 1 and z equal to 2 are the two poles. So the first one is it contains no poles, so it's analytic here. You can expand this one in a Taylor series. In the second one, you have to use a Laurent series, and for z greater than 2, you have to use a Laurent series again. So the problem is done. We might discuss it in one of the discussion hours, but I'll just leave it for you. I'll just leave it for you, and you can find the expansions yourself. I strongly suggest that you try them out. Okay. So this completes our discussion on complex variable theory. This is a very quick recapitulation of things that you have learned in complex variable theory. I think many of you have learned these things earlier. We have just recapitulated them, and now we will see how we use the theory of analytic functions, all that we have learned, how we use it in elasticity to solve problems in plane isotropic linear elasticity. Okay, that's in the next lecture.